A very good morning to one and all. I welcome you all for this session number 28. In this session, we will derive Lagrangian equation of motion using D'Alembert's principle. Note that Lagrangian equation is a reformulation of Newton's second law of motion. So in previous class, we learned D'Alembert's principle, which states that the resultant force acting on a body together with reversed effective force, they are in equilibrium. Mathematically, it is given by summation I is equal to 1 to n Fia minus Pi dot into delta Ri is equal to 0. The main objective of this session is to derive Lagrangian equation of motion using D'Alembert's principle. No, this is for holonomic case. By the end of this session, you will come to know how to derive Lagrangian equation of a motion and Lagrangian equation. Derivation of Lagrangian equation. So let's start. We know D'Alembert's principle. Mathematically, it is represented by summation of I is equal to 1 to n Pi dot minus Fi dot into delta Ri is equal to 0. Substituting for generalized displacement, we arrive at this expression summation j is equal to 1 3n minus k into summation I is equal to 1 to n into mi Ri double dot minus Fi into dou Ri by dou Qj into delta Qj is equal to 0. Here we have two terms. Fi is the applied external force and this is a reversed effective force. Now let's simplify term by term. Consider second term, which is given by Fi dot dou Ri by dou Qj into delta Qj. Considering this to be Qj, then Qj term will be equal to summation I is equal to 1 to n Fi dou Ri by dou Qj, and this Qj represents generalized force. Now let's consider second term, which is mi Ri double dot into dou Ri by dou Qj. We know that differentiation of a product rule is given by differentiation of uv is equal to uv dash plus vu dash. Using this principle and rearranging terms, this expression can be expressed as differentiation d by dt of u into v, that is mi Ri dot into dou Ri by dou Qj minus mi Ri dou Ri dot by dou Qj dot. Note that this term and this term can be expressed in terms of this. It is given by d by dt of differentiation dou by dou Qj dot into summation of I is equal to 1 to n of mi Ri dots square. So if we differentiate, we arrive at this term. Likewise, rearranging this term we arrive at dou by dou qj of summation I is equal to 1 to n of mi ri dot square. Of mi ri dot square is nothing but kinetic energy term. So the kinetic energy as a function qj dot into t is given by summation I is equal to 1 to n of mi ri dot square. So substituting this term to be t, the above expression reduces to d by dt of dou t by dou qj dot minus dou t by dou qj minus qj into delta qj. If it is independent of delta qj, this second term will set to 0. First term set to 0, that is d by dt of dou t by dou qj dot minus dou t by dou qj minus qj is equal to 0. Now we know that qj is a generalized force. If generalized force is a conservative force, then using potential we can arrive generalized force using Fi is equal to minus delta V. That is, by potential you can derive force. If that potential is a function of only on the position but not on the velocity, that is, if the potential is a velocity independent function, then dou v by dou qj dot will be set to 0. Then qj will be equal to dou v by dou qj. So substituting q in terms of dou v by dou qj and using dou v by dou qj in this term, we arrive at an expression d by dt of dou L by dou qj dot minus dou L by dou qj is equal to 0, where L is equal to T minus V, where T represents kinetic energy and V represents the potential energy. Note that dou L by dou qj dot is represented by P, which is a generalized momentum. So this expression is known as Lagrangian equation of motion. For a generalized force, this Q, this 0 should be replaced by capital Qj. So in this session, we learned how to derive Lagrangian equation of motion using D'Alembert's principle. Now let's have a small MCQ session. Question number 1. The Lagrangian equation of a motion for a system is equivalent to Newton's laws of motion. Question number 2. The Lagrangian function is defined by, we are saying L is defined as L is equal to T minus V. So answer is option B. Question number 3. Pi dot in D'Alembert's principle represents, so that is a reversed effective force, then the option is C. Question number 4. Qij in the derivation of Lagrangian equation by D'Alembert's principle represent, you know that Qij is nothing but a generalized force, so the option is B. Question number 5. In Lagrangian function, T represents, you know that T represents kinetic energy, V represents the potential energy, so the option is answer C. Question number 6. Expression for Lagrangian equation of a motion. It is d by dt of dou L by dou Q dot minus dou L by dou Q is equal to 0. So this is for a conservative forces. If it is a non-conservative force, at 0 should on the right hand side should be replaced by capital Qj. So the option is answer A. If the potential is independent of the velocity, then the differentiation of velocity with respect to differentiation of potential with respect to velocity is 0. So option is D. Question number 8. d by dt of dou L by dou Q dot minus dou L by dou Q is equal to 0 is an Lagrangian expression for. This is expression for only conservative forces. So its option is C. Dou L by dou Q dot in Lagrangian equation represents, we know that it is momentum. It is generalized momentum. So the option is D. Question number 10. Lagrangian equation of a motion is derived using, we derive this equation using D'Alembert's principle. So the option is C. So in this session, we learned derivation of Lagrangian equation using D'Alembert's principle. Hope you enjoyed this session. Thank you.